So yesterday we left off talking about how Ka and Kb of a conjugate base were related to each other using this expression Ka times Kb equals Kw. And we derived that expression and proved why you can use it. And today I want to show you the application of that. So some things that you can do with that and some salt hydrolysis problems that are going to be applications to knowing the pH of a solution that contains a salt. So I'm just going to put up an example and we're going to work through it quickly. And that example is going to be what is the pH of a 0.25 molar, and we'll do Na3PO4 solution. So one thing that I would recommend when you have this type of problem is that you have a salt. It's not an acid or a base necessarily right off the bat. You have to decide that. I would suggest that you go ahead and predict first if it's going to be acidic or neutral so that you can check your answer against that. So with sodium phosphate, this is actually one of the ones that we did yesterday, and we tested it with the indicator. So I'm just going to go through this, and I'm going to use yellow to show Na plus 1 coming from NaOH, which is strong. So that means Na plus 1 will not act like an acid because it comes from a strong base. PO4 minus 3, however, comes from HPO4 minus 2, which is a weak acid. So that means its conjugate base, PO4 minus 3, is going to act. So we're predicting that the solution is going to be basic. So we're anticipating a pH of greater than 7. And so that's just a good thing to go back and we can check that to make sure it makes sense. So I want you guys to picture when sodium phosphate hits the water, so Na3PO4, when it dissociates, we're going to get 3 Na plus 1s, aqueous, and we're going to get a PO4 minus 3, aqueous. And since we know since we know that the original solution is 0.25 molar, we can know the concentration of those two ions as well. So since the Na3PO4 to PO4 minus 3 is a 1-to-1 ratio, I know that I'm going to have 0.25 molar PO4 minus 3 in solution because it's 1-to-1, and I'm going to have 3 times that amount of sodium, 0.75 molar, in solution. But the thing is, the sodium is not going to do anything, we said, so that doesn't really matter. What we're concerned about are these 0.25 mole per liter amount of this conjugate base that should act like a base because its parent is a weak acid. So this is going to act like a base in solution. And so what I'm going to show you, you don't have to do this every problem, but I think it kind of helps, is if I were to take PO4 minus 3 and have it act like a base, water would be the acid, and so water would donate one of its H plus 1s, so we will get HPO4 minus 2, and that would be the conjugate acid, and then we would have OH minus, and that would be the conjugate base. And so the reason I do that is because if we want to figure out the concentration, if we want to find out the pH, the key to that is finding the concentration of H3O plus, which is related to the concentration of OH minus 1. So that's really our key to solving this problem, is by finding out the concentration of hydroxide ions. If it was a weak acid, we could find it with the H3O plus concentration. So that's really what we want. And I'm going to set up a Kb expression so that we can find that. So I'm going to clear all of this out. And so we will have KB equal to, we had the OH minus 1, and that's really what we're interested in. And we had the HPO4 minus 2. And that was all over the PO4 minus 3. Okay, so what do we know and what don't we know? Well, right off the bat, we know the concentration of PO4 minus 3 because that's what we went through at the beginning of the problem. It's 0.25 because it's the same as the salt with that 1-to-1 ratio. I have no idea what OH minus 1 is, and I have no idea what HPO4 minus 2 is. So in fact, the reason I can put X for both is because they're a 1-to-1 ratio also. So if I make X amount of HPO4 minus 2, I'm going to have exactly the same concentration of OH minus 1. It's a 1-to-1. So I'm going to replace this actually with X squared. And KB, we are not given, but we can look up the Ka of that's not what I meant to write. The Ka of HPO4 minus 2 on your Ka table. So that's easy peasy lemon squeezy. That is 4.5 times 10 to the negative 13th. And then since I know that Ka times Kb equals Kw, I can divide Kw by Ka. So if I divide Ka by Kw by Ka, I'm having trouble with my screen, that's why I'm stuttering here. So if I take Kw divided by Ka, I should get Kb, which is going to be equal to 1 times 10 to the negative 14th divided by that 4.5 times 10 to the negative 13th. And when I do that, Kb ends up being 2.22 times 10 to the negative 2. And so now I have all the pieces I need to solve for X, which remember is the concentration of hydroxide ions. So if I multiply each side by 0.25, and take the square root, X should come out to be, well gosh, I don't know what X turns out to be. Just a second. That turns out to be 0.0745, and remember that's the concentration of OH minus 1. So if I take the negative log of that number, that's going to give me the POH. So I want to subtract that from 14 when I get done. And when I do that, I get an answer of 12.87 as my final answer, which is above 7, so it is basic like I had anticipated. And so that all checks out. So that solution did turn quite purple yesterday, so that's why. Because we dumped in some of that sodium phosphate, and the phosphate ion did its base thing, and it left us with a pH of well above 7. So I want to have you guys work with those numbers some more today, and then we can wrap this up and get it assessed and tested next week sometime. So I hope you have an amazing weekend, just amazing, 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 and I will look forward to seeing you on Monday. All right, see you later, bye.